The easiest example of an accelerometer is a spring. Yes, a plain, boring spring. Suppose you put a spring into outer space, empty space, flat space. It'll have some extension. Now, if you tie that spring to a rocket and that rocket blasts off, what's going to happen with the spring? It'll expand so long as the velocity of the rocket changes. Why is that? Well, as Newton taught us, force equals mass times acceleration. So if you accelerate one end of the spring, that creates a force, and that force stretches the spring. You can measure how much it stretches, and from that you can calculate how much it was accelerated. This example tells us three very important things. First, you can use a spring to measure acceleration. It's not the only way to do it, and maybe not even a particularly good one, but it works and acceleration is measurable. Second, you cannot, of course, use the spring to measure the velocity of the rocket, because velocity in and of itself is a meaningless concept. You can only talk about relative velocities, not absolute ones. This brings us to the third and most important point that we learn from the spring. Acceleration is not relative, it's absolute. You can measure how much you're accelerated, for example, with that spring, and you can tell when you're not accelerated.
Smartphones come equipped with accelerometers. If you fire up an app that shows you the data from the accelerometer, like this one, you will notice something. It shows about 9.81 meters per second squared upwards. Here I'm moving the phone to show which axis is which on the screen. So your smartphone believes that you are constantly accelerating upwards. Why? Let's look at how an accelerometer works. A simplest one would just be a weight suspended on identical springs. No acceleration, and it will just hang there in the middle. If you accelerate it, the weight will get pulled in the direction opposite to the acceleration, and you can measure the deflection and figure out the acceleration from there. The accelerometer shows an acceleration upwards because it is accelerating upwards. Okay, but there is a bit of an issue with this, isn't there? Consider two people, one in Spain and one in New Zealand. On a globe, those two would be on the exact opposite sides of Earth. If both of them were accelerating upwards, they would be accelerating away from each other, so the distance between them would have to start growing at some point. But as far as we can tell, the distance between Spain and New Zealand is, well, fairly constant. The spherical model of the Earth have to be wrong.